Ok, bienvenue. Merci Viviane et Margot pour l'invitation, pour la conversation. Je parle un petit français lentement. Je voudrais parler avec vous après la conversation. Je pratique avec toi. Okay, so welcome. My name is Mike. Great to be here speaking. Again, thank you so much for the invitation. I'm going to be talking about concurrency today. And just want to talk a little bit and add that there's lots of great conferences coming up. Feel free to talk about those things with me after. But as we get into concurrency here, how many folks first use C++ in their day-to-day programming? Fortunate enough. Okay, about more than half here. Makes sense. How many folks do concurrency work? Done so. Okay, good chunk. Okay, I gotta be on my toes then. So today's talk will focus on some of the fundamentals. Feel free to ask questions at any time. You can try again in French or English, it's fine. But I want to give sort of a fundamental introduction, and I'll move a little bit quicker during some parts if I see the audience is nodding along. So we're going to do a recap of just some of the basics, starting with threads and jthreads, and then talking about those with data parallel problems, so for performance, something we care about. Then I'm going to talk briefly, sort of towards the closing of the talk on thread pools and producer-consumer using condition variables. So again, some foundational stuff, but as we take each little part and understand it, we can put them together and make interesting patterns. And that's sort of the goal for you to think about what I have this tool and the very basic fundamental mechanisms. What I'd also like to do with you is show you how to look at parallel programs in GDB. How many folks have used GDB? Okay, excellent, très bien. How many folks have used UDB and know what that is? Undo, yeah. Okay, so something new. I'll show you a brief demo. I know Greg, I think, had spoken before with maybe Tony as well, or just Greg. But very cool tool, very useful for concurrency debugging. So that's a must-have. So I'm a teacher by trade at university, and I also do 3D graphics programming. So that's also my passion. So contract work when I'm not teaching. And maybe you'll find me running around Paris. Those are my other hobbies through this time here. All the slides and everything will be on my website. If you search my name, you'll find this talk in the slides. And the code as well, which is also important. So there's the abstract, you know about that. I want to start off just showing a video game, just quick, as I said, as a graphics programmer. So I care very much about performance and things that I think just look beautiful. These simulations of virtual worlds, there's lots of stuff going on. There's artificial intelligent agents running around. There's physics simulations going on, sound in different places. Things are crumbling and being built up. It's very fascinating, how much work our computers do and how much we can get out of them. So thinking about all this stuff that's being computed every millisecond, or sometimes they're thinking about it at nanosecond scale, is quite impressive. So I just think it's a fascinating domain. I saw somebody reading a book on video games as we were at this meetup, which was cool. And of course, the sponsor, Margot, does very cool and works on challenging problems, as they're mentioning. But what comes with some of this stuff with graphics and so on is the challenge of how do we get performance out of this. So I've highlighted notes from a nice talk at the Game Developers Conference. You don't have to read the notes or pay too much attention to the screen here. But basically what they're highlighting is that every little section of the world is being simulated on a different thread. So something interesting is going on, some interesting engineering there. So that's what we want to talk about today, those basic primitives. And of course, where to start here, I always think of things here, serving coffee, so to speak here. So whenever I think about concurrency, well, I think about how's the fastest way I can get my coffee or tea, right? We want to line up and make sure that we're doing something like this. 2 machines is better than 1. This is by Joe Armstrong. How many folks have programmed in Erlang before? Heard it? Okay, 1, 2, okay. Excellent, all right. Well, this is from the late Joe Armstrong. Built that language, which was basically a message passing language. So lots of concurrency built in from the start. So anyways, the way we normally program, as you folks know, is sequentially. One instruction after the other. That's how we're sort of taught, right? Write one line, and we can see it sort of execute. And then usually, the way I think about things is on a functional granularity. So one function executing after the other. Again, makes sense. Here's a sort of call stack that you would get from your main function, calling another function. Either way, it's sort of a sequential execution, even though you're kind of hopping around your source code. Still doing one thing at a time. But obviously, as you might imagine, being able to do two things at once is going to be better for things like speed and just sometimes even just reasoning about a problem, being able to separate it out into different pieces. All right. So as I mentioned, the coffee problem here. So I'll go ahead and just kind of look at this diagram here. It is kind of interesting to think, and I'll ask since maybe folks have done concurrency before. This example here, this is what I mean by concurrency. Two lines forming for one coffee machine. Parallelism, two separate coffee machines, two sort of different thoughts here. And then, of course, the sequential line here that I added. This illustration that's getting longer. Now, why is this fast, or what's going on concurrently, or could be going on when we're getting ready for coffee? We've only got one machine. I mean, we'd probably like this, but why is this also still pretty good?
Once you grab the cup.
Pardon?
Did you grab the cup somewhere?
Yeah, maybe you're grabbing a cup on the side. Yeah, yeah.
Just have to maintain one machine, like just fill one machine with water, worry about just one thing.
Yeah, even as a resource, right? One machine here. I don't need 50 to maintain, right? I could be kind of over-compromise or over-synchronize. I'll show you that later. You could have folks, getting stuff out of their wallet or whatever while they're getting ready for the line. Versus here, it's always the first person in line kind of fumbling around and blocking the whole thing, right? This idea of kind of blocking what's going on. So again, that's just something to think about with concurrency. And we actually get a lot of this for free, right? A lot of times when maybe you open a file or something, things start spinning up. Yeah.
If we look at the current example in supermarkets, what they do is one queue for several machines. And it's not displayed there. So it seems to be the most efficient now for real human beings, actually.
Yeah, one queue, many machines. Interesting. Yeah, maybe now we could sort of think about that. Is the latency or the highest cost thing getting through the machines here? Maybe we don't care about the line so much, or
I don't know exactly why they do
yeah.
that, but that's the current change in the supermarket. Of course, sometimes the queue splits in several small queues for each machine, but there is still just one big queue for all those machines.
Yeah. Well, that's so they can put the good snacks next to you to pick up while you're in line.
Maybe they want to make sure that there is not that each person gets served with a limit on time. So maybe it's not the most efficient globally, but maybe it's the things that minimizes the problems for one person.
Yeah, absolutely. I mean, this is something to think about. This is the wonderful thing about concurrency. We can think about, our life is concurrent, right? Our world is concurrent. There's multiple things happening, right? You're all listening or maybe working on something right, while at this talk. But there are these real world analogies. Supermarket's a great one. I often use that in class. Coffee machine, airports and so on. I'll give you a little spoiler for what I saw outside. There's a lot of concurrency going on. I'll show in the presentation. So again, and it's thinking about where that sort of latency, where is the bottleneck? Where might folks have to synchronize and communicate? So that's exactly, concurrent thinking. That's where we want to get to. And it is interesting to observe the different supermarkets in different countries as you travel around and see what they're trying to optimize for too. So, I'll give you a short definition here. Concurrency and parallelism, they're different things. They're kind of used interchangeably. Something that is happening in parallel is as well concurrent. So concurrent meaning, multiple things at once. the trick is, or how I try to separate out what I mean by concurrency, though, is that there's sometimes there are tasks that have to be waited on. You're usually sharing data, so there's some sort of order or partial ordering. We might have to wait for things. Again, like the one coffee machine and two-line example. Okay, two lines concurrently conform. You could be doing things, but ultimately there's a shared resource, that coffee machine, that you want to get access to. Parallelism is sort of how we like our problems, right? There's 40 or 50 chairs here. Everybody just gets their own spot and can do whatever they want independently. That's also nice. No real synchronization needed. But using both of these terms, concurrency or parallelism, why we care, again, usually performance. That's usually how I'm going to motivate it, but sometimes it is by function, right? Our world being concurrent, resource management, these things that you folks mentioned. So here's just, again, some more ideas about it. And again, as mentioned, I'm going to be just talking about the concurrency that's on your CPU, but your things like your hard drive or network devices, right? There's going to be concurrency and maybe different ways of thinking about them on those devices, where you folks might have expertise. Now, continuing to motivate this just a little bit, there's this great quote: "Performance is the currency of computing." Has anybody heard this before? Anybody know where it's from? It's from a really thick textbook. Does anybody have this textbook? Popular. Every undergrad in the US has to read it, or pretend to, I guess. Yeah, this one, CLRS book, Introduction to Algorithms, from Charles Leiserson, professor at MIT. But I love this saying that he has. He says, performance is the currency of computing. And you can often buy needed properties of software, again, with performance. So again, just a little bit of motivation for trying to think about performance on your systems. That's, again, a motivation for C++ as a language that can give us performance. Right? You can buy your customers more, save time, save energy, etc. Here's another one for you. How many folks have seen this article or heard it? Yeah, the free lunch is over. Okay, Herb Sutter, another person you might run into at conferences like CppCon and so on. Can anybody sort of summarize what's this free lunch mean? We don't get to eat anymore? Who's read the article and can cut? Yeah.
I haven't read the article, but I think it refers to when there was, let's say, thought unlimited performance just with better hardware. Now we are reaching the limit and we have to utilize more resources from the same hardware.
Yep, 100%. Used to be, used to be the case. We could say, oh, you want your program run twice as fast, just wait a year. Just go, your hardware is going to get faster. You don't have to do anything as a software engineer. No, not so much, right? We have different hardware paradigms for this.
There was only Java developers who thought that so they had unlimited resources for running their software.
Pardon, I missed the first part.
Sorry?
I missed the first.
There was only Java developers who thought they could have unlimited power to run their program.
Yeah, right. We don't have unlimited power. Again, that's why we're getting hired as C++ programmers, right, for great companies, or thinking about these things at the least in your language of choice. So we don't get as much free performance on the CPU these days. Okay. Why? Some architecture stuff. Now, again, I'm going to kind of quiz you on this, so to keep us moving along. I'm going to show you this chart here, and just shout out if you've heard this person's name or seen this. This is the first diagram I'm going to show you in the next slide. You just have to show this on a concurrency talk. So let's see here. Well, let me show you the chart here. Oh, I got the name. Yeah, Moore's law. Yeah, you got it. All right, this idea that our CPUs, we're getting more transistors, right? Twice as fast, or roughly doubling how many transistors we get every 18 to 24 months. Still largely held true. Yeah, comments for folks who know about this.
I mean, it's slowing down. It was maybe at first, but at some point, like, transistors can only get so small.
Yeah.
Before you start breaking the quantum tunneling value.
Yeah.
That's the topic.
Yeah. Oh, it's going to be on the next slide. Does anybody know what that law is called? Because this is the actual problem, how tiny the transistors are. Yeah.
I don't know what's the exact name.
It's like the Moore's law, so like the one to double, but then there's another phenomena where you can't have so much power gets shut off.
Yeah.
all the transistors turned on at the same time. So that's
Yeah.
the limitation.
Yeah, so I'll fast forward us to this. So Moore's law is, we've had great innovations, Gordon Moore from Intel, companies like NVIDIA, Apple, pick your favorite semiconductor company, TSM and so on. They're able to pack more transistors on a chip, which is really cool. But the issue is, as mentioned, because of physics, right, things are getting closer and closer. And if we were in a class with my students, well, I wouldn't really do this, but it would be fun to try. I'd say, now get really close together and packed together. What would happen? Other than being a little bit uncomfortable, right? You get really warm, and then you get a little bit anxious, I guess too. But the issue is, right? We get too much heat being generated, and that draws a lot more power to cool the systems. We also have to kind of keep track of things. But this is the idea, Dennard scaling. So this isn't necessarily a linear algorithm. It's more for a power draw, right? This is like power the energy from our computer, more of a quadratic function. Heat becomes the problem. So that's the big issue, if you ask folks. Now, depending on who you ask, right, where their expertise are, they're going to tell you, yeah, we're going to get down to 3 nanometers, and then we're going to stack things. And they're probably right. That's not my expertise, but regardless, the trend is we still have to think more as software engineers. Can't just let the hardware folks do it anymore, unfortunately, for our performance. Yeah.
Anyway, there is a big trend with the reducing of the carbon footprint and energy consumption footprint, and making more optimized code. I think is a good way to follow these trends. The green IT, I think, is good.
100%. I mean, everybody's got one of these, right? That's always draining battery, and that we're having to charge. And mine gets really hot when I plug it in or use it too long. And as you said, green energy for the planet, for data centers, everything. This stuff matters. As I flew over here, it's a 6-hour flight. It was nice that I had my this laptop and my Mac, actually. The battery lasts because you can put it on a low power mode, right? So it's using maybe different cores that are a little bit slower. So all these things that matter for performance here. So let me get us to our next laws here. Now, interesting enough, there's another problem. I'm just throwing problems at you so far, and then we'll try to fix something. But who's seen a chart like this? I don't know what to call this. This processor memory gap here, right? Processors, as I mentioned, yeah, Moore's law, we're still getting faster and faster. That's great. But our hard drive, those aren't exponentially growing. That's this bottom line here over time. It's just growing a little bit faster every year. Okay? So if our CPU is really fast and good at handling data, it's not going to do us very much good if our hard disk is very slow at populating that data. Right? So this might be, trying to make a similar analogy to the supermarket. If we say, well, if you go to the cash register, you can check out in 1 second. But if it takes our customers an hour to walk there, and they're getting slower over time, that's kind of what's happening here, right? It doesn't matter how good the processor technology is. Okay. So does that sort of make sense? So if you've heard this term of being sort of I/O bound, this is what we mean. But again, these are where things like concurrency and asynchronous programming can help. Okay, last law for you. This one I didn't spoil. I'm not going to spend too much time on it, but does anybody know this law? There's variations of it. There's only a few laws. Amdahl, yeah, Jean Amdahl. Does anybody know what this is saying here? Give you a chance to think about it.
Like optimize the best case or something like that.
Yeah, has something to do with optimizing the best case. So this part here, latency, we can think about the performance, how many customers we get through the checkout line, so to speak. P, I'll tell you, is the parallel portion. So maybe how many cash registers we have. And S is the serial part here. So it forms, this kind of ratio. Basically what it's saying, again, not going to quiz you on any math here, is if you've got a problem that's inherently serial or sequential, where folks must go one at a time, it doesn't matter how much parallelism you use, right? There's just going to be parts where you're blocked. Okay, we've got how many? No, 2 elevators back there. That's the best we can do, right? That's sort of our constraint. But we can still have something that's parallel here, right? 2 elevators going down at once. So that's the basic idea here. So that's Amdahl's law. That's the other one you have to know. And you should also know, these are laws from 1960, 1970. There are variations around them that model things maybe more or less accurately. But that's in short what you have. So we're going to find out, and I'm going to actually show you an example today. Sometimes it's not better to actually use concurrency. You can just forget this talk, go enjoy, find the pizzas early, and enjoy. Because sometimes your problem is just inherently sequential or better solved that way. Okay, and that's a whole other software engineering trade-off. We'll get some great speakers to come, or folks here. Well, folks here are going to sign up for a talk, I'm sure, and give that talk, right, about how to write simple and clean code. Maybe a lightning talk today. So anyways, that's Amdahl's law, that idea. Now, again, good news. Hardware folks have been helping us for a long time, so this is just a little aside here. You do get things like pipelining and these types of things for free, usually. So I'm not going to touch those parallelism things, but again, worth knowing here. Okay, so they're in the slides for you to reference. Okay, so let's get into threads here. And again, I think I saw 60 or more % of folks here rose their hand, said they had done some threading or concurrency work, something like that. But again, to get everyone on a common baseline here, we're going to be talking about the first part here on concurrency, which again, you can think about things like an orchestra, right? Not every instrument's trying to play at the same time. Otherwise, that's loud noise. But from a computer science perspective, you'll think about things like your memory allocator. There are bottlenecks there. How many folks use malloc here? Okay, probably, right? Or behind the scenes under new, right? There's probably malloc. How many folks have used an arena allocator? That's like, okay, I see hand up. So that's the idea of having sort of more mallocs, like behind the scenes in malloc, right? Somebody's got to be handing out the memory. Hopefully they're doing that responsibly, maybe in parallel, but there are other strategies, right, that we can do concurrently. So just a few thoughts there. All right, and then I wanted to show this picture here because, again, out in your train yard right over here, trains, ultimate example, right? You have the parallel rails, but you don't want them driving, 2 at the same time in the same place, of course, but they are taking turns, coordinated, and so on. So I love the trains, in Paris in particular, because I just take the trains everywhere. So anyways, so that's the idea here. So, I think it's useful to understand too what concurrency is and this mechanism of a thread. Okay, so the basic idea with a thread is, well, you have another little diagram like this, instruction by instruction, that's processing. Same idea with a thread. It's got its own instruction pointer, so it's its own totally separate entity that's executing one line at a time here. Okay. Let me give another view of it here. Give you a chance to kind of look, or I'll point to some things if you can't see them in the back. Again, thread, a lightweight process. So you can think of it like having 2 brains on your computer or your program that's running. Here's the first part. Here's the second brain here. They've got their own registers, again, own instruction pointer. The data, however, is shared. Okay, so if you have a global variable or you heap allocate something, all that's going to be shared. Okay, but your threads will have their own local data. There are other things where you can kind of specify how this data is shared or not shared. Again, new C++11 things, you can put thread local storage, meaning every thread gets its own copy of something. Not going to, there are ways to control things. That's one of the great things about C++. You can control basically whatever you want. You just got to know about it. But this is sort of the picture of threads here. So again, if you load some shared library while your program's running, if you do new or malloc and allocate some memory, each individual thread can access it. But the actual functions that the threads are executing, any data allocated there, those local variables are still just local. Okay. Questions about that idea? The key idea. Folks have seen maybe a diagram like this or thought about it in the same way before? Some head shakes? Okay. All right. So here's sort of, again, just a model for thinking about threads. Again, having threads, I think about them like little factory workers coming into my factory. That's the main process there and helping me out with whatever task I need. All right. So on threads versus processes, what I'll just say or sort of summarize is threads are lightweight processes. Okay, they exist within the actual process that's running and are sort of maintained there. That gives them some advantages from a performance standpoint versus if you have a bunch of different processes that are running and communicating over some other channel. Okay? All right. All right, let me ask you folks this one. When should you use threads? What are some reasons that you folks are using them for? Or what domains? Anybody doing games or finance or web? What are folks?
You want to actually join the data at the end in one place.
Okay.
Like, I can give an example from a previous job where we'd have to connect to multiple microservices. And then just get the data for each one given a certain key and then aggregate it in one single place. That's a great idea for threads.
Yeah.
Because you want that memory of those different executions in one place. Processes would be when you know those executions are somewhat independent, I would say. You're handling requests from two different customers or two different clients. Whereas threads, it's probably, let's say, the same client, but the request has multiple levels or multiple dimensions.
Yeah. That's a great point in the, when to use them, right? Again, I'm talking about performance today. I'll show some performance stuff. But as you said, there's different isolation or protection by keeping things in one process, right? Versus a thread sharing pretty much everything, right? If I go back to this slide, right? We're sharing all the global data. So if you want to aggregate something, a bunch of different rows of data that you're filling in, that's a great use for threads. Yeah, perfect. All right. Perfect. I think that's good. Other folks want to share the domain? I'm just kind of seeding so I know who to kind of talk to and ask to when we're eating pizza. Thread questions. So feel free to, or you can grab me later too. I'm not going to call on anybody randomly. I don't like that either. So, all right. So we get an idea of threads. For now, we're just going to think about threads on the sort of C++ perspective. Again, I'll leave the wall of text here for you later to read. There's things like green threads, operating system thread, kernel thread. We're just talking about thread that's part of your process that you execute today. GPU threads and stuff. I'm not going to talk about coroutines. We need a full talk for that. So let's get into some threads in modern C++ here. All right, so we have thread. That's the most important thing. C++ 11, this is a reason to use it. Don't have to use, pthreads or boost or Intel thread building blocks. But there might be reasons, as you're going to see in this talk, whether it's the interesting like quirks or maybe there's something lacking in the standard library when it comes to threads, that you might still use those libraries or build your own. Right? So a lot of those gaming examples I show folks, implement their own threads. But if you kind of understand the fundamentals, that is something that you can do here. I do recommend threads, and a lot of folks do recommend it from the standard template library just because they tend to have good portability, right? They are something that's tested. Again, that's going to vary on your domain that you're working on because threads, as we're going to find out, depend on your architecture a little bit as well. Okay, so we've got lots of support for interesting things in threads. Okay, so let's go ahead and include a thread here. Again, a separate thread of execution. I'm going to go through maybe this example of launching a thread just sort of by pictures here, but let me highlight the important things. First, if you're on Linux, you got a Lincoln pthread here. So I've done that. And then just the visual execution again. What's going on here? So we've got our main thread, just for our main program. Right, we've always got one thread that's running. And it starts doing some stuff. And it says, oh, I found this line here, my thread. It's going to start executing. And my thread takes in the address of this function test, which you'll see at line 7 to 10 here. It's just a function that prints something out. And that's all you have to do to launch a thread. Okay, so for those who haven't seen it in C++, anything that's callable, you can put it there. Std function, address of something from a functor, whatever, anything that can call is in the thread here. Okay, so there's our new thread. And then we get a separate box off to the right, which means some other thread doing its own independent execution, okay, from that function's start here. Now both are going to start simultaneously, depending on your architecture executing. And then in our main program, you're going to see this line here, join, which basically is synonymous with wait. Okay, and that basically says, hey, this thread here is going to block our main program from making any forward progress until my thread communicates otherwise, right? It terminates effectively and is done. Okay, so my thread's going to do its printing, then it'll return, and then we can move forward with our execution. Okay, so these are things, if you've done this with processes in C or something, right? You're doing a wait when your thread joins. When your thread terminates, that communicates again back to the main thread that you can proceed forward. You're unblocked. Okay. Questions about this example? Folks okay with that? All right. My folks have done threads. You're like, yeah, that's the hello world of threads. There it is. Okay, so as I mentioned, you could do things with lambdas. So you could put a lambda in there. That's fine. And move through that. What if I want 10 threads? Okay, this is where we start getting into the patterns and some more interesting stuff in this talk here. Okay, so let's this time launch 10 threads. Okay, so again, that's what I'm going to do in this block. It's just a for each loop or for loop, pushing in 10 threads, executing the same lambda function, and it's going to join them. All right, so I'll highlight it. And for those of you folks in the back, you've got good eyes if you're reading that. So I'll try to give my narration. But this is what we get. Maybe we'll get some help from folks in the front. What's going on here? Is this all right? Here's our thread. Argument passed in. OK, so it's just printing off the argument, the thread ID. So the thread ID is just some long integer, something unique. Hey, it happens to be the same one every time. Okay, 0, 1, 2, 3. Hey, that's nice. It executed in perfect order. What happened here? Did I mess something up? Yeah, I'm blocking myself right here, right? So again, just on that join, blocking. So this is a nice example to show about, one, how things go awry, and we're going to have to debug it. I'll show you some debugging as we proceed. But the second reason I want to just show you this is because I want you to think about this join as a sort of way that you're synchronizing your program. You are saying stop here. So it is some mechanism that you have. Now this isn't what I necessarily intended here, right? I didn't mean for an in-order execution, right? I could have just done this without threads. But again, it's showing the point of what join is here, okay? To have some synchronization here. Okay, so we saw what was wrong there. Great. And this would be a form of over-synchronization, or a way to think of it, right? So we have too much blocking in our program here, okay, that we didn't intend for. Can anyone else who's done some concurrency work tell me other forms of I don't know, ways that we block ourselves too much? What's our other primitive that we have? A lock, yeah. So we can over-synchronize with locks or block or impede ourselves as well. I'm not going to talk so much about locks today.
Also without writing code, but by misusing the cache of the processor.
Ah, OK. So there's other ways. Interesting. Do you have it's a little bit of a spoiler. Do you have a name for that term?
I can't remember the name right now, but it's
Does anybody know what happens if I'm writing to the same cache line in 2 threads? What's that called?
That depends. It's like
For sharing.
False sharing. Yeah. Okay. You got it. Yeah. A plus plus for everybody. All right. So we'll see what happens. I mean, we're going to be done with the talk in like 2 minutes. Everybody, everybody already saw my slides. Great. So anyways, the fix here is to move that join somewhere else, right? Move where you're going to wait or block something. Okay. So you're creating some sort of barrier there. Okay. And there are actually primitives, barriers, and latches for exactly this thing for multiple threads. All right. So, if you don't want to mess up the creation of the thread in the join, there is something called a jthread in C++20 that you can use, where you're basically forcing your synchronization to wherever the destructor is called. Okay. Have folks use jthread here? Okay. So a new one. Good. I want to show you guys some new stuff. So, pretty similar example here. I'm just kind of highlighting around and for the recording so you can check out as well. This way you don't have to worry about join if you just want to join or attach to the main thread at some point. Okay. If I don't join to the main thread, right, the main thread's going to terminate, and then there'll be all these like zombie threads, we call them, sort of alive and wandering about the world saying, hey, where's my main? Right. So they're alive, but they're not really alive. So zombie. That's the idea here. Okay. All right. So that's your sort of. I gave a talk at CppCon, and there's been lots of other great talks at a lot of these conferences that Vivian mentioned at the start. If you want to look at all the different mechanisms for locking, I'm going to save that for you a little bit so we can talk about some new stuff. But if you want to see again those sort of ideas or are new to C++ threads or want to review, check that out. But what I want to start moving us towards is talking about teams of threads and doing something data parallel, performance, right? What we tried to motivate at the start of this talk. So that's kind of captured by this idea here that we're going to have a main thread. That's like our team leader, our captain. Pick whatever sport you like, if you like sports, or a band or something. That's the person leading, and they're going to command the 4 J threads there to do something, and then they're all going to meet up, right? They're going to aggregate the data into something useful. All right, so we've got this J thread that lets us maybe do things more interestingly or easily. Here's the problem I'm going to give you. We're going to have this team of threads here. The main thread's going to spawn or spin up 4 other threads and then push them into the main thread. And they're all going to write to different places in memory. Okay, so if they're all writing to different places in memory, do we need locks to synchronize? Probably not, right? If I tell 4 people to go to different places, right, you're not going to bump into each other. So that's exactly the idea. So I'm kind of skipping locks today for a little bit, I guess. So that's the idea. Okay. So here's the resulting code. Again, very tiny. I'll make it a little bit bigger. Basically, I'm just going to initialize some shared memory here. And again, a little bit of slideware, but some global data, maybe something allocated on the heap. Maybe it's managed or you're requesting this from somewhere. But just somewhere where you have some shared memory that threads have access to, right? Global stuff and stuff on the heap. Here's going to be our worker threads. So I have lambdas, one lambda here. It's just called a addition worker, and its job is to go through indices in an array and add them up. Okay, and I've been very, very careful to make sure that each thread's accessing a different indice, right? So one row in a 256 integer array, right? Thread 1's going to modify the first 64 elements, the second thread, the next 64, and so on. Okay, make sense? All right, great. And we're going to do 5 iterations of this to make it interesting, or more interesting, I guess. So it'll go through the array with each of the worker threads 5 times, adding to them. Okay, so here's our result. Here's what we get, something that looks like this. So here's 256 5s, each of the indices incremented here, and it looks like it worked fine here. Okay, or at least in my initial test, right? We just did some test here. But I want to know if this is going to be faster, and I don't really have a good benchmark here. This took 0.004 seconds. So let's crank up the workload a little bit. So now I'm going to do this 50,000 times, just as another test here. OK? What are folks expecting here? Should we see each value at 50,000? I mean, that's what I want to see probably, right? So now I have at least 50,000 threads that are going to execute and do this work, which is just adding one to an index. So what I get here is, crash. OK. What happened here? What do folks think happened? I messed it up. I broke it. I came all the way to France to break things. Oh no.
Too many threads for the system?
Yeah, too many threads for the system, right? So we do have hardware limits on these things. So 50,000 iterations of creating 4 threads, that's 200,000 threads. I don't get 200,000 times faster, right? It's unfortunately not always how it works, at least not on this particular problem here. Okay. So what's the issue? As you mentioned, if we sort of look at the exception that's thrown, there's resources temporarily available. If you kind of do a deep dive into this, you're going to get something about there not being enough threads here. Okay, so what I've highlighted in that text is 200,000 threads is too much for my machine. Okay, I'll try to run one of these in a moment here, and you'll hear my fan start spinning. That's one warning sign. What's going on here?
Even if it works, it's probably not going to be faster than a linear program because the cost of creating a thread is probably more important than the work done by the thread.
Yeah, interesting. Yeah, interesting. I was going to say, did you guys hack my computer and look at my slideshow? All right. Well, let's look at this really quick. I want to do at least one quick thing with GDB here, just to show you. When you get into these threading problems here, let me find my example here. This one I'm going to call. Let me try to make it nice and large for you here. Threaded programs are pretty hard to debug, just by the nature that you're doing lots of things. But we do have tools for them. Okay, so I don't want us to give up hope here. So I'm going to compile that program. Right, I'm going to run it carefully. It's going to crash. And then what I'm going to want to do is just load it up into GDB. Okay. If you can't catch it all here, that's okay. I'm just going to spend 20 seconds on it, so it's on the recording. But let's go ahead and load up our program here. A lot of you folks said you're using GDB, so maybe you know about the text user interface mode here. But I've already sort of messed up if I launch GDB and try to debug this system. I've got to prep GDB to do the multi-threaded debugging because it is a little bit more of an expensive operation. Okay, so I'm going to quit GDB. I'm just going to launch GDB itself without the executable afterwards here. Okay, so there's no processes, but let's see. I got to type in this set mi async. Okay, on. Okay, load my executable, which was program. Okay, there we are here. And then I've got to do this other thing here, which again I got to look at my set scheduler locking on. Okay, what does that mean? Well, if you have a program with many threads and you want to break in GDB or stop or halt your program, that's just a helpful thing that'll stop all the threads that are running. Okay, this program, it's not going to matter so much, right? There's just 50,000 things being blasted, and the program's going to crash. But we want to sort of find out where or why. Let's see here. Got to check my cheat sheet. Set scheduler locking on. Oh, it says it can't support this command for some reason. That's okay. And then I want to just set some breakpoint. I think 37, and if j is greater than 50, something like that here. Okay, so basically I just want to go through this program, next, 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 next. And I want to get somewhere in this loop here where my threads are and try to figure out what's going on. Okay, that's the basic idea, right? So you can start debugging your threaded programs, something like this right here. Okay, and I can do next and next and next, next. And then immediately we can kind of see there are some problems with this pattern. What else do folks notice that's kind of weird here? It's subtle. We have the issue of spawning 50,000 times 4 threads, so 200,000 threads. When do those threads destruct? They're jthreads too, right? Here. Do they live a long time? Oh, that could be one potential problem here. Okay, so we have to kind of think about sometimes when we're collecting things like threads. Threads are movable, which is nice. They're not copyable, so we don't have to worry about excessive copies too much. But we are moving them into this vector data structure, which what happens when we push back in a vector. Right? It's going to keep doubling every once in a while, right? So that's going to be a problem. And then, well, we've got 200,000 jthreads in a vector, and then they're just going to kind of live there, right? So that's also kind of an interesting problem to think about. Okay, now I'm not going to run this 200,000 times, but you get the idea here. Okay, how are we doing on time? Okay. All right, so the fix immediately itself, one fix that's easy is just to move in the scope threads here. Okay, so that will only, we won't carry around this huge allocated vector of threads. They will destruct eventually when they hit their scope because we don't need them necessarily to be long-lived here. Okay, so that's one potential fix here. If you want to find out on your system the actual limits, there are ways to query that. And again, depending on your domain, that may matter. If you're building a web server or something, you want to find a nice number here. And we can actually query some of these things in C++ as well. Right, you've got your system. So I've got a Unix command at the top to kind of look at that. My Unix system allowed 15% of my maximum 500,000 threads. So it's like 30,000 or something threads I can do. How many threads do folks think I should launch if I have a 10-core machine? 25, was 25,000 or 50,000 a good number? Right, we said they have a cost, right? We saw little pictures. Probably not, right? So again, this is lore or myth or story, but a okay metric, right? Like the laws we talked about at the start. 2 threads per 1 core is reasonable, right? That's a reasonable place to start. I came up with that one through sage wisdom. Someone wiser than me, I suppose, told me that, and I've sort of carried it through. But I actually measure 2 every once in a while. And also, if you, I'll show an instruction in C++ that'll tell you roughly how many threads you could do. Okay, so there's built-in stuff in the standard for that. Okay, back to this point here. Sequential execution is sometimes better. So some folks have already commented on that. I did run this sequentially. If I just have a worker that's adding 1 to an index of array, I tend to get much better performance. Okay, because thread creation can be expensive and the destruction itself can be expensive as well. Okay, less complicated code, so you got to measure these things. At the very least, you still might want to write some sequential code as a unit test, right? You have something to compare it against to see if your results are okay. All right, so even with just 4 threads, it's still too expensive. Now the big issue here and why we often get that expense is how much work each of those workers are doing. Okay, and someone mentioned this before, this term, a bunch of you did. You shouted out false sharing. Okay, again, just a little bit of an aside, but here's that nice C++ instruction that'll tell you exactly how many threads you should have. On my machine, it's 20 because I have 10 cores. It just happens to be, again, it might vary. And the other thing is how much data fits in a cache line, basically. Okay, so if I'm working with data that's in core 3 from some thread, and it's got to constantly read in a bunch of data from into the L1 cache, but thread 2 is doing that, and some of that data is overlapping. This is what's known as false sharing. I'm sharing the data, but they have to agree on it in the hardware, what that listing of data is. Okay, it's another full talk. I'd love to come back and give that talk, but Scott Myers does it. He did it 10 years ago and 10 times as well as I could. So there's a link for that on, understanding your hardware. And that's one of the tricks with concurrency, right? To not get carried away with the fancy stuff, but actually understand what's going on. So here's an example where I launched too many threads with not the right data size, and it takes, actually I do the right data size of 64 bytes at a time in my array, but I launch too many threads and it still takes 15 seconds. So I'm way worse. Okay, so anyways. Okay, so I'm getting closer to the end here. Let's try to solve some of this problem here. So we've kind of identified some of the things we can do with threads. Let's remove the idea of thread creation itself here. Let's create what's known as a thread pool. Okay, what's a thread pool? Well, that's the idea that you just allocate all of your threads at the startup. Okay, just as it sounds here. Same sort of thing our operating system does, right? Our operating system has a pool of threads, and you run a bunch of processes that are sort of assigned. So we can do that too. And that should get rid of the issue of creation, and then we have control over when we destroy things. So a first attempt at this is to just refactor the code. So that's what I've done here. You can take a peek at it, but the key thing is I've just allocated in a fixed size array of 20 threads here. Okay, so it's a starting point. And again, I'm using these hardware instructions to figure out exactly how many threads I need in a pool. And the idea is I'm just starting to pool out some of these building blocks that I have that we've talked about, like threads and jthreads, thinking about when I assign and create things and just having a fixed number of these. And this gets me pretty much the same performance as before, adding this level of abstraction, but it's kind of neat. I'm kind of building out this structure, something that looks kind of reusable and a neat idea. A thread pool, and then maybe I can just assign it tasks. Okay, and you're a constructor, or you can provide a function that executes something. But in order to fully realize this, we have to do a little bit better, right? So here's one piece. But again, threads, once I execute them, right, they just sort of execute and then they terminate. I need to keep them alive some way. So all of my threads in theory should just have a while loop, right? While true. That's one way to keep them alive. What's the problem with that? If I launch even 4 threads that are running infinitely, all right, they're just going to be spinning forever. Or I need to figure out some way to stop them, I suppose. And that's where we get into condition variables. Okay. How many folks have used condition variables? Okay, good chunk. How many folks like them? No, yeah, I mean they're kind of strange, right? And this was the most fun part, writing the presentation. I'm like, how do I break this down? Condition variables, because there's always like 3 parts you need to it. Okay, again, sorry to throw the wall of text at you. You can look at the slides. Just want to talk through it, but a condition variable. The basic idea is it's a signal, right? Think of it like a traffic signal outside. It's saying, you can go, but you can't go. That, in fact, is another pattern, okay? One of the things that I'm very excited about coming up in 6 weeks, the Olympics, right, coming to Paris here. The relay races, do you folks watch either swimming or running? That's kind of how I think of condition variables. Someone's running with a baton and they hand it off. And I say, go, and they can do their work, okay? So that in itself is a pattern, and it's very useful. The most common pattern, which I'll show in code, and I'll actually run it in a moment with the undo tools, is conditional variable as a signal pattern. Okay. Now, how you want to combine that and so on is sort of up to you, but it tends to work nice with this idea of a thread pool. I have something that's running infinitely, and I want to signal when it should do that or not. Oh, yeah, hopefully you can see better. Okay, so condition variable example. You need at least 3 parts, sort of, and then a 4th, I guess you need somewhere to share the data for your condition variables. So you've got a lock, which again, apologies, I've kind of skipped over locks, but again, just think of them as a key. One person owns it. The condition variable itself, and then a variable, a literal variable, true or false, an integer or something that you can evaluate to true or false. And then maybe a shared queue of data or collection of something that's shared. Okay. So let me just show this example here. Let me just run it here just so you can get an idea of it. This is simple CV. And I'm just going to highlight and narrate. This is what I'm highlighting here, a producer thread. All you have to know is that it's producing data and putting it in a queue, just like a factory worker. Okay. And then this is a consumer thread, someone else, down the factory that says, oh, there's something in the queue, I grab it, right? So again, same grocery store analogy, someone at the cashier and then someone, bagging the groceries. And that's the idea here. Okay, let's actually run it. Let's see here. Let's compile it. I'm compiling with C++23, which is in pretty good shape these days, minus modules and some other things, I guess, as was mentioned. But here it is, right? We're just consuming the value from a shared queue, 1, 2, 3, 4, completing the task. Okay. Now again, let me show you what was happening here. In the producer, I have a for loop for 5 items. I go to sleep for 250 milliseconds. That's how often I'm generating work. And every time I generate work, I push something into the queue, and then I notify somebody. I say, hey, there's work to be done. I've just produced one more element in the queue, and you're pushing it in. Okay. And then the consumer, in the meanwhile, is blocked. We've got this sort of while not ready here. Okay, so something that's going to just keep happening and happening and happening. And it's also blocked on this lock here as well, right? Which could be, this could be some sort of spin lock where it's occasionally checking, but only sort of when we're waking it up and saying, hey, there's something going on here. So in this way, I don't know if I should have taken a survey on who likes conditional variables, because they are great, right? They're great for performance, because you're not necessarily, there's ways to use it so that you're not always, like if you implement a spin lock from scratch, you could just have a while loop that's checking forever, right? This we can actually put asleep on the hardware more efficiently. Okay. And then our consumer is just going to pop and look at something on the queue here. Okay. Okay. So I want to run this. Let's see how I want to run this. Let me run it with, so something cool that you can do. Let's see here, downloads, undo. I wanted to show this just because this is really cool, I think. That program that I just ran, you can actually record what was just done here. So I'm using this tool by undo, and this is how I get to know Tony and Greg and stuff. I just love debugging. And this is exactly our program that we did. Now this is a pretty trivial program, which is fine. But what's really cool is if we take a look at it, it produces effectively this trace here. And this works on programs at scale. I'm sorry I didn't bring I should have made a server or something, I don't know, with thousands of threads or something. But it does a pretty good job working on scale here. And then the cool thing is, instead of running my program here, let's say that there was something weird here. I can just use their other tool, UDB, which is their time travel debugging stuff, and I can run it just like GDB here. Okay, I can look at layout source. Here it is. I can put a starting point. I could go into the thread, the next thread, and I can say, okay, how many threads do I got? Info threads, and then you can start kind of exploring. And this is just the replay of what happened. Okay, and I can kind of debug through that, which is really neat. That's my go-to tools. First, jumping into GDB and just seeing what happened when there's a crash. And then if I can, I try to capture, record, and then investigate. Okay, so hopefully that's interesting. Hopefully at least that's something new for you folks if you're already thread experts. But just wanted to show that stuff there. Okay, so that's a condition variable. Kind of went through the code here. Okay, and then I debugged it here. So I want to kind of wrap us up because we're running out of time here. I want to keep us on track for pizza. And I showed the live recorder and UDB stuff. Okay, so what's the point here? I showed you condition variable, thread pool, and then we sort of got somewhere where we could say, well, what if I combine these two things and have 20 threads or something that are running indefinitely on some condition, and they just get signaled and can maybe like pick up work or be supplied a function, a pointer to some work, and that's exactly the point, okay, for creating some sort of pool. The world where I come from, we call these job systems, so that's just another key word that you can look at in games and engines and so on. Here's a pretty decent thread pool implementation, if you want to take a look at code and how they do something with packaged tasks and promises here, doing asynchronous programming, which is very neat. And it's a C++ 17, so pretty modern library here. Because, and again, this is looping all the way back to the little gaming example that we started with. You kind of want your program, at least in a game, to look something like this, where you're doing some updates here of all your objects that are running around. You don't really care what in order, but in parallel, right? That's why we started with the data parallel stuff and the concurrency. But you sort of want these sync points every once in a while where you can block, have some sort of mechanism. So maybe that's your condition variable. Maybe it is a join. Maybe you're spawning a thread for update. If the work's big enough, right? We got to figure that out. And then you can do like the next task and the next task and so on. Okay, so that's just one way to think about it, to have these barriers, parallel, and then pick up and sort of refill the work in your thread pool. So it's really, I find it very fascinating and fun to play around with these tools. Sometimes I find it frustrating too, and that's why I share the debugging stuff. And if you'd like to learn more, this is sort of the, how do you do these from scratch? Like if you want to implement your own lock or your own thread, which is pretty cool. There's a bunch of these patterns from this book, the Little Book of Semaphores, where they just use semaphores for everything to implement latches and barriers and mutex and everything from scratch. So that's neat. I'll put more stuff on this concurrency YouTube, software design stuff. But here were some really good talks on in practice in game engines, again, because I come from that gaming world. And of course, Sean Parent on just concurrency applied. In Sean's talk, this is like in 2013 or 14, I want to say, he was building basically effectively like a thread pool or like a, what do you call it, like some sort of task manager, basically, where you could assign jobs to. So that's a neat talk to watch. Alrighty, so with that said, thank you very much. Merci beaucoup. Happy to take questions, and I'll be around. Talk to me about anything, yeah. So thank you.
Is there any question?
Yeah.
At what point is it good to have thread pools? Because the cost of starting a thread is the duration.
Mm-hmm.
So if you're going to check every instance after a few seconds,
Yeah.
there is a wait for looking up. So are we supposed to be aware of our workloads? Then you're efficient enough that your wait period is small?
Yeah, so coming from this world, I get to cheat a little bit because you do have a budget. You say you have 5 milliseconds to do all the graphics. The AI gets 2 milliseconds or something like that. So if you are fortunate to have a sort of well-defined budget like that, that's great. You can kind of get away with that. If you don't, I don't know if I have a good answer. It just sort of depends on the domain. The classic kind of measure and see what workloads make sense. You can always break these things down more. You can think about, again, it's always sort of that trade-off of maybe you want more sequential stuff, or maybe you want lots of threads and then you aggregate the data later. Do you have a domain in mind that you're thinking about?
No, I was just thinking if what's a good use case? Is it are we supposed to be very much aware of our workloads? Then it's a good use case, or if you're not sure about what kind of workloads you're going to have, then this metric is going to be all over the place. So you don't have a good benefit.
Yeah, I mean, another sort of famous talk, and I tend to agree with it, it's this data-oriented design talk by Mike Acton. Have folks seen that? It's probably the most famous CppCon one. I always show it to my students. But he would just come back to you and say, oh, if you don't know your data, you don't know what you're doing. So it is kind of one of those, know the workload, know the machine. Because there's stuff on this Linux machine that might not have been true even on some of your Windows machine, as far as how much control you have over scheduling stuff and these types of things. But that is kind of the advantage. And again, just knowing about the threads is useful. We have these other tools like coroutines, which are coming in, which might also be another interesting thing, right, where you can sort of yield and pause execution, right, and sort of schedule those tasks as you need. So yeah, that's a long-winded answer to I don't know. You just sort of have to know the workload, and it's changing. Yeah. Yeah.
In my opinion, if you just create statically threads, like you want to have two different stuff running at different frequency during the full duration of a program, you can just use a thread. But as soon as you want to dynamically create threads, and you don't know the number at the beginning, a thread pool is something to consider.
Yeah. Again, games, I always say they should know, right? So there's other tools. I skipped over it, but you can look at things like, malloc stats was something that I showed in GDB. So you know how much you're allocating. So if I know in a game I have 50 characters or something, I might know that means 50 threads for each of them or something like that, right? So we can always usually measure and gather that data. And as you said, if you don't know, and it's going to be totally dynamic, then you try some pool, I guess. Yeah.
Maybe
Yeah.
is there any plans to add thread pools to the C++ standard? I don't know if you.
I don't know. Does anybody have insight on that? Is anybody on the?
There are some plans to add many stuff. So many stuff that was kind of progressing slowly. Basically, what's the name of this pattern? They want to create a full framework of sender and receiver.
Yeah.
And one of the possible building block of it would be a thread pool, but it would go much beyond, and I've never read those papers because that's not my domain. But I know that there are some plans to do some stuff like that. They made some progress recently, but they already made some progress a few years ago, and each time they're reaching completion, there is a new pattern that appears, and they start from scratch again. But maybe this time is going to converge to something, and when that's ready, they don't just want to have a thread pool. It's very nice building block, but it's probably better at too low level for some stuff, and they want to have something much more coherent, and that's why they struggle to have this and the rest of our stuff.
Maybe we can get string split before that.
We have something for string split.
There's something in Boost, but
not in Boost. With Ranges, it's not directly string split, but it's close to being simple string split.
I think there is some pool in Boost as well, a thread pool as well. So you could try those out. Most folks will say, "Why are you using threads? Don't write that code." It's like, well, I mean, sometimes you just have to, right? But there are some libraries that are probably pretty decent starting points too.
The thread pool is not enough because, for example, you have to send data to it, so you need the queue to send data. So it's not a place that you can use totally in isolation efficiently.
Yeah.
But yeah, I think the library like ASIO embed this kind of mechanism in the release. It's really integrated, and they can handle event queue where you feed them, and it's already the queuing system and stuff is already embedded in the library. For what I've said for what I've seen when I used them, it was sort of already integrated. The whole thing was integrated and working out of the box. Wow.
Yeah. Was there another question?
Yeah, I was just thinking about stud async
Mm-hmm.
that allows to launch a function asynchronously.
Yeah.
And the documentation says it might be run on a thread pool.
Yep.
And it returns a future.
Yeah.
So it's implicit.
Yeah.
Depending on the
I know for stud async.
Probably not.
Yeah, I think the same with if you look at any of the parallel algorithms, if you run them with I think unsequential as the policy, I think it says might be implemented as a thread pool. So maybe, again, I'm not sure which compilers. MSVC is mentioned probably is the furthest ahead these days, actually, with stuff.
And it's using TBB as a backend.
Oh, if it's using TBB, yeah, probably. Thread building blocks. Yeah. Yeah. Question.
I have a question about say false sharing.
Mhm.
That's a concept that's new for me. I wanted to know, is it a symptom of like a poorly designed program, or is it more something it can be avoided with like something?
Yeah, that's a good question. Is it a symptom of poor coding? I mean, I think it's more just about the access pattern. I mean, there certainly are tricks, right? Like padding your structures to make sure they're always, 64 bytes and these types of things, which, again, we could sort of think if those are good coding practices or over-engineered, or, I mean, it's one of those things where you just kind of profile for and you say, hey, this, like in perf or something, you probably wouldn't recognize it right away from the speed, but hopefully you're looking at cache misses and hits at various points and would probably run into it. I think it's more just a access pattern. Yeah, I don't know if other folks have run into where they've captured it. I'm always thinking in powers of 2 and the number 64. And again, that's not a hard set number. That's like for this machine, and it's different for like game consoles or this. Correct. Yeah, and that's what can make it really challenging. Same thing with like when I showed the thread limits or like how many is a good. So yeah, it's machine to machine. Some of those properties, again, you can query. Again, you can query all those. I've seen a lot of library code that does use those queries to determine like how big, or how many threads to use. Yeah. Yep. Yeah.
I've seen some people using vtune to detect false sharing just by measuring the metrics of how many cache misses you have, and when the number is growing a lot, it might be a reason of it might be because of false sharing. vtune, the tool to monitor the execution of many properties on the processor.
Yeah, I think it's a free Intel's tool.
Yes, it's from
freely
Intel.
available, or
Is that Google benchmark also measuring cache misses?
maybe I use perf on Linux, and you can see the page faults, cache misses, these types of things that are good hints sometimes.
And it's not only the number of misses, but it's more the frequency of misses. Because the number of misses, you don't know.
Yeah.
It's big. Is it normal? Is it not normal? You don't know. But if at some point you have, in a short period of time, many misses, maybe looking at the layout of the data could be interesting.
Technically, you can detect that with the peak of the request for ownership, message on the between the two, which has the underlying root cause of the cache.
Yeah.
Yeah, but that wouldn't be full sharing because I mean full sharing is for the L1 cache line, so different can share the elements on the cache line. Yeah. Okay, just the cache line generally speaking.
Yeah. Yeah, it does get tricky because, I mean, right, you've got 2, 3, maybe 4 cache levels on some machines. So it's possible you just have to sort of know where it's going to get shared. Usually I'm looking at the smallest increment and trying to control for that. So again, 64 bytes. There's a really good talk at ACCU by Mathieu. I don't know if he's spoken here. Mathieu Rapport. Yeah, Rapport. That's going to be coming out soon, and he talks about all these tricks that he uses for data-oriented design. So.
Maybe another way to detect this kind of stuff at a higher level is just run in one thread, run in 4 threads. If you don't have a 4 times speed up, it means that at some point something is a problem. If you know the problem, it's good. If you don't know the problem, maybe you have this kind of stuff.
Yeah, that's right. I think in Scott's talk he shows like, yeah, it should be about 4 times as fast, but as soon as you notice it's not, 3 something, you profile, yeah. That's the hint, yeah.
Usually when some new threading things get introduced, is looking into debugging capabilities important thing? Like you showed, like how to do debugging for parallel threads or with pools, or is it just like should someone be concerned about that? Is performance worth it to not have good debugging options?
Oh, I mean, like on the tooling side, yeah, I wish we had very good tools. You know, there's this stuff, like again, I think live recorders, a good step in the right direction. I think visualizers, there's things like flame graphs you can do to get sort of performance readings and see where you're spending time. I don't know if that's answering your comment, but yeah, more tools are usually helpful for performance. In the game world, with engineers that I've worked with, the debugger or the profiler is running 100% of the time. And maybe it's just a sampling profiler, you know, because you need more performance or whatever, but there's always some tool running in the background so I can catch these issues and see where they're being introduced, which is kind of interesting. How many folks run with a debugger on or profile 100% of the time? It's probably worth trying. It depends on your system, I guess. Yeah.
There is a canonical way to integrate threads into a select or conditions and select. You know, when you're waiting for a file to be readable, for instance, a socket.
Oops. Let's see. I have an example on my CppCon. So if you launch a thread asynchronously, you can check the status. So that is something that you could do. And the way async works is, you know, it generates a promise that you'll get a future result back. So you're going to be blocked. But what you can do is just sort of periodically check what's the status while you do other work. And that's, again, I don't have any insight, but would I've built like a loading like bar or something like that.
Yeah, I was thinking more about the thread pools when you have to serve a bunch of requests and you're waiting to have a request.
Oh,
so I know there's the follow the
oh yeah, as far as like scheduling and these types of things. That's a whole world. I mean, I know a little bit about, so you have some control over like thread priority, and there's some stuff like that you can do if you know you have like high priority tasks or long running stuff that you're able to measure. There's this whole other side of things in like load balancing your work and being able to query which threads are like busy and which tasks. Are those useful things, or is it just about querying like how much?
It's just about querying if the condition that it can be woken up by
Oh, I see.
a thread, but you don't want to have a thread wait. You'd like the kernel notify you with select that you are actually ready to read.
Oh, I see. Yeah. So I've got in my CppCon talk, I've got the async example, and I know how many bytes the file is, so I've like checked it so that I'm not notifying every like, you know, all the time. I think I need to think about how often, otherwise, it's because it's the same thing with locks, like how often it's going to wake up and check. That might be based off of like priority that you can set on the thread or something. I don't know, actually. I don't know 100%. Other than engineering the system where you're like, okay, the file's almost ready, and then notifying more frequently. Yeah. Oh, yeah.
Is there a good practice to handle the exception within
Exceptions. Oh no. Yeah. I mean, this is one of the. I mean, one of the things I'll say why people like jthread is because it's sort of wrapped in free, right? So it'll destruct if you have an exception, and you won't be blocked anywhere, or have these sort of zombie threads, which I talked about. That's probably the classic thing. I mean, if you're wrapping these primitives up, you want a constructor and destructor that'll be called when an exception's thrown. I need to think a little bit more on, or maybe look at CppCon to see where does no except and these types of things show up on threads. I don't know too much on that. I want to say Scott Myers has something in the first effective C++11 one on concurrency there, on exception safety. But I don't know if I don't know actually if he talks about the threads. Yeah, that'd be a question.
With DTC and under nomic system, if you throw an exception, you cannot catch it in the main thread. So it's quite good practice to have a try catch in the function thrown by run by the thread, and after you can use an std exception ptr to rethrow to the main thread. That's one sequence to handle it.
Oh, interesting. So capture it in a thread and move it back to the main one to handle. Yep, that makes sense. Yeah, yeah. You would know better than I. Yeah, some of you. Yeah.
And I think if you use std-async and you use a feature to get the response of the thread, if your thread has a swap, then you will get the swap back. Yeah, but I was thinking if you have any people on the thread. For that, I don't know what you can manage. I just know this example for when you use feature, because it's a bit different to know that feature can pass on exception.
Thank you very much.
Thank you. Merci.